Good morning. Welcome to the ZoomTown Experiment, episode number 61. This is a continuation, so to speak, of the last two episodes, wherein I'm trying to wrangle in the continued problems I'm experiencing with the Zoomie not positioning correctly or accurately enough. Now, I hinted last week that in the last episode, that I was onto a different motor with an integral encoder, and I've done bench testing on it, and I'll show you that in a little bit. But first, let's start with looking at the results. Now, if you remember from a few episodes ago, the measurements I was getting, or the deviation I was getting in a distance of about 12 inches, was in excess of 0.4 inches, so that'd be almost 10 millimeters. So let's see what we got now, and then we'll discuss how we got to this point. Back here on the test track, or actually in ZoomTown, I've got everything set up over here. This is my endpoint right here, the start, or from your view, the left edge of this white line. Right there, hopefully you can see it as a pencil mark. That is where I'm going to align the starting point of the Zoomie. The Zoomie is going to travel 2 rotations of the wheel, or we'll say it's 10.5 inches, I think, off the top of my head. That part's irrelevant, but what is important is that it gets to this line, or very close to it, every single time. It will also not be doing any steering, so you might see it wander to the left or wander to the right. That itself is not a concern for this test. This is our first run. Might have gone a little far. I'll measure that up. You'll notice too that here are the actual encoder counts for channel A and B, left wheel, right wheel. The right wheel's going a little bit faster, so you get a little higher count number on it. And again, that would be due to no effort is being made in steering. We'll go ahead, run another test. Okay, that one is a perfect 0. Interestingly, our numbers are closer too. That one stopped short a very tiny amount. Perfect 0. And we'll continue this for about 10 more tests. That repeatability just by eye looks a world different than what I was getting with the AS5600 encoders. Now, a lot of that deviation could be lost or generated in backlash, with it walking or driving off direction. Other influences are involved in here that I have to account for. But let's just stick with the raw data to see if we're making progress. In this example, we ran 21 test runs that you saw over there, and I was documenting measurements by using a scale and by eye, so it isn't ultra precise. But considering before I was getting numbers as much as 400 thousandths of an inch or nearly 10 millimeters, or a little over 10 millimeters, I'm okay with that. Well, let's look at what we've got in graph. Now here is our big number there, and then from here we've got very small deviations throughout this range here. And this seems to be the more consistent data set. If we look at the minimum value where it stops short, 70 thousandths of an inch or 1.77 millimeters, that must be that sample right there. Our max was that sample. Our average, overall average of all of this was negative 0.007 inches or 0.169 millimeters. That is way better than what I was getting before. It is not as good as I want, so please don't misinterpret this, but it is a huge step forward. And it is, we'll say, a practical test in that all of this data is collected with the Zoomie physically moving on the track where it normally would be. Only difference being I'm just moving it along the yellow line instead of the gray line. No other reason than that, just it was the convenient way to do it. It was easy for me to get the mark spots on camera for you to see. Let's continue with a little discussion about the information in the data sheet. Coming down, of course, a lot of this is not real clear as to what they're explaining, but there are a couple things that'll help us understand what's going on. I don't know what a Holzer signal is, but I know that the encoder's got 7 poles in it. So I would get 7 pulses per rev if I'm just measuring either the rising or falling edge of each pole. Here they define pole count as 7, but if you're measuring rising and falling, I'm assuming is what that means. Or if you're measuring A plus B, that's what that would mean, either 7 or 14 counts per rotation of the motor. This one here got me in trouble. 3K3, 3.300 ohm pull-up resistors. The Pico did not like that at all, and it created a lot of really weird problems. So what I did, I started out testing without any pull-up resistors. Then I added the pull-up resistors, and suddenly weird problems started happening. I took out the pull-up resistors, problem went away. I did that twice in 2 different layouts, and the problem kept happening. It seems to be behaving fine with just the internal pull-ups that the Pico has, which are, I think, around 50K, something like that, 50K ohms. That was an interesting little adventure there that took me down some really nasty paths and wasted a lot of time. Let's see, we got basic pinouts. The output, it is can be utilized with quadrature decoding because it is a quadrature signal, and you see that here. I didn't want to utilize that because I have no purpose for it, and the complexity of dealing with decoding the quadrature data only to get the addition of directional information, forward or reverse, was a waste of time for me. All I need is for every time I see one of those signals to mark that as a distance traveled. And I know which way the Zoomie's going because we're telling it which direction to go. So that, I went away from the quadrature decoding. I actually had it all working and then just thought, why? It just wastes time. I'll explain that in a minute. Here's their output circuit for the device, and they're showing again the 3.3K ohm pull-up, and they're noting that you can be working with either 5 or 3.3 volts. And that's all that's really of importance, I think, at this point that I can rely on extracting from that data sheet. Now, how does all that play into what we're doing here? You'll have to excuse my silly little drawing here. I did this in Google Sheets or something like that, and slides, I think it is. But it was a quick way to get an image together so I could explain what all that means if you're not familiar with encoders. There are 7 poles. 1, 2, 3, 4, 5, 6, 7. Think of the poles as little magnets. They'll have a north and a south pole. I don't care about the orientation, all that. That's irrelevant to this discussion. There will be 2 Hall effect sensors here and here, and they're usually indicated by channel A and channel B, and they detect those poles. With that, the Hall effect sensor can count the number of these that go by in any given period of time. And if they're spaced accordingly, you can also get quadrature output out of the 2 Hall effect sensors, and then with that you can determine direction of rotation. I wasn't concerned about that. Now I am using interrupts within Micropython, and it's detecting currently the rising and the falling edge. But for discussion, let's just say if I'm using one channel and I'm looking at the rising edge, for every rotation I would get a count of 7. If I'm detecting the rising and the falling edge, for every rotation I would get 14 counts. If I added in counting up the channel B highs and lows, or rising and falling edges, I could double that again. So it would go from 7, 14 to 28. At some point you just look at it and go, what value is that extra tiny amount? And that's what we'll get into in the next slide here. Let's look at what we've got with 7 magnets. The motor is 100-to-1 gear ratio. The encoder is looking at the motor, not the output shaft. So every time we look at this number here, the 7, it's actually 700. What does that mean? If I'm only counting rising on one channel, that's 7 times 100, or 700 pulses per revolution at the wheel. That's really what we're concerned with. We need to, of course, know the data in between, but we need to know how far the Zoomy will move with each pulse from that encoder. Now, if I measure both rising and falling edge, I get 2 counts per magnet. So that would be 2 times 7 times 100, or 1400 pulses per revolution at the wheel. Now let's extrapolate that out to distance moved. Again, same motor and encoder, 7 magnets, 100-to-1 gear ratio, 100 rotations of the motor for 1 rotation of the wheel. The wheel's circumference is very difficult to measure, but it's 5.2622, the best I can measure. And if we're just measuring the rising on one channel, 5.2622 divided by 700 equals 0.0075 inches, or 0.19 millimeters. That's been my goal, is to always be less than 0.5 millimeters. So that alone, that particular resolution is good. Now, if I'm looking at both rising and falling, of course, I would get twice as many pulses for the same distance, and that would drop down to 0.0038 inches per pulse, and that's 0.095 millimeters. Again, a very good number and a very high resolution. And if you're not familiar with the scale of this, just to give you an idea, this 0.0038 paper, typical 20-pound printer paper, is about 0.003 inches, 3/1000ths of an inch. So that's how small of an amount we're looking at here. Now, there is one thing with this configuration that is very different than the previous one, and this was another reason why I went down the path that ultimately failed. backlash is measured. Now, backlash is the play between the gears or any mechanical devices. Screws, gears, all these devices have some amount of backlash. These little inexpensive motors can have quite a bit. I would say on the wheel, once I've been running them in, I would say about 3 or 4 degrees of rotation, maybe not quite that much. That's a lot of backlash, and that's a lot of distance, and you have to account for that when you're doing motion control. Well, in the case of this, almost all of our backlash is within the gearbox. So you've got your motor, the gearbox, and the wheel. The encoder was on the AS5600 encoder was on the outboard side of that wheel. So I'm measuring the exact rotation of the wheel. Whether there's backlash in this gearbox or not, I'm looking at the wheel. So I saw the exact movements. Now that also created problems in developing the code and everything, but I won't go down that rabbit hole right now. Now let's see the difference between the old system and the new system. Backlash is not measured in the new system. The integral encoder is attached directly to the motor. So the encoder is seeing what the motor is rotating. It does not see any backlash that's generated in the gearbox or at the wheel as we were seeing before. So that's a huge difference, but in practice, when I go from forward to reverse, it's very rare. Often it'll be a pivot turn. It'll be when I'm pulling across an intersection, backing out of a driveway, things of that nature would be where backlash would introduce itself. Anytime direction is reversed. In practical, I could actually calibrate for that and factor for it in all motions. At this time, I don't know if it's a problem, so I'm going to just leave it on the back burner and not account for it yet, because it does add a fair amount of complexity, and I don't want the program to get overly complicated again. Moving along, we're going to take a look at the test rig that I've been using to test out the motors. I have 3 pair of motors, 6 total, for me to keep playing with and experimenting with. This guy right here has a mechanical issue in it, which is not uncommon for these types of motors. And this one was one of the expensive ones, but is what it is. It could also be dirt in there too. These things come in filthy, and I usually soak them in a solvent, clean out the gearbox, blow it off really good, inspect it with a loupe, and then lubricate it with a light oil and so forth. And I did not do that on these. But anyhow, I'm switching out motors throughout the testing to introduce that variable. The wiring is pretty straightforward. It's very similar to what's in the Zoomy itself. We just got our cables coming back. Some of them connect directly to the Pico W. We've got a MOSFET over here that is being controlled by a PWM output, so that I can vary the speed of the motors and control that, because I want to have a decelerate when it comes to a stop to make sure I'm getting consistent stopping points. Over here I've got an oscilloscope hooked up so that I can monitor what the signals actually look like. And there has been a problem that pops up every once in a while, and I don't know exactly what the cause is. But it's as if the counts appear to be right when I look at it on the oscilloscope. But in the Pico, it seems to be reading tens of thousands of counts when it really should have only read maybe 100. And I don't know what's causing that. So I was trying to observe what's going on with the oscilloscope. I've also brought in this guy. Let's see if I can get him. This is a logic analyzer that I bought a long time ago, and I haven't used it in probably 10 to 15 years. I dug that out, and I was also monitoring everything with that during this testing. One other thing I've got on the test rig, there's a wheel here with a magnet on it, a Hall effect sensor, and I'm detecting every time the wheel rotates 360. I also use that to establish a starting point. You'll see the wheel rotates slowly till it activates the Hall effect sensor, then it'll move off the Hall effect sensor, then the test will run. I've been running 100 revolutions for this video and demonstration. I'll probably tone it down to like 20 or something, and then we can look at the data and see what we're actually gathering here. I did want to just briefly go through the program. It won't be line by line, just importing the libraries that are needed, not much, defining some of my interrupt handlers for the left wheel A channel, left wheel B channel, right wheel A channel, etc. Presetting some values for the counters. This is setting up the interrupt, and here's where I'm setting up IRQ for rising or IRQ for falling. So we're catching going up and going down on the signal. This is our Hall effect sensor, this guy right here that's seeing that magnet, and every time that magnet falls, what we're going to see is it'll print out the current counts for left and right wheels, A and B. And that is again running on an interrupt. I'm running a frequency for PWM at about 300, and I experimented up and down, and it didn't seem to change much behavior beyond that, so I'm just going to leave it there. We're going to start out spinning the motor at a moderately low RPM, 39,000 on the PWM duty cycle, and we'll do that until we see the signal for the magnet. That'll transition to on, and that you'll see a bright red light there. Then we'll move again a little bit faster past, with the magnet past the sensor, and that'll be our reference point. And then every time it goes around and that signal hits, then we'll print out the count values. Again, presetting things. This is the main loop running. Once we get to our distance to go as less than 200 counts, we'll lower the speed so that again it's behaving like a deceleration, and I can trap that end position more accurately. And then when we get run out of distance to go, we capture the LA count. I was using that for another thing, nothing right now. And then I set the duty cycle to 0 and the motor stop. So with that, I will get the program up out of the way. We'll scoot that up. I'll make sure the oscilloscope is running, the camera, everything looks good. So we'll start with our first run with this test rig today and see what kind of behavior we get. And you'll see down here what you want to see. These two numbers in the left columns should be identical. The two, or within reason, 1 or 2 counts off, and then the same in the right 2 columns. This is left wheel, this is the right wheel over here. If you look at the oscilloscope, the data actually looks pretty good there. Nice square wave. I'm on a multiplier. My probes are set at ×1, not ×10. But I'm still getting a decent, nice square wave there. And the speed, you can kind of tell by this right here. It's saying 927, 928 hertz. That's when it's triggering the encoder signals. And by the way, that's also what the quadrature signal would look like if we were decoding that. They're shifted by about 1/4 of a phase from one another, and that's how you can determine rise forward and reverse depending on who's rising first, etc. But these are the tests that I've been running over and over and over again. And now I can pretty much bank on the fact that both motors are not running at exactly the same speed. If they are, it's rare. And in this case, looking at the numbers, I think they ran at the same speed for pure luck. I don't know what to say. Normally they don't. So now what we'll do, we'll take a look at this data and in a spreadsheet and see what that looks like. Now that we've got some sample data, 5 test runs in that last test, let's take a look at what the graphing shows us. And right away you'll notice this strange one, which we talked a little bit about, or we saw. And what this staircase effect is, this would be where we see a flat like that, would be when the Hall effect sensor does a double on-off. And that's due to hysteresis when you're on the edge of the magnet and you're getting into the body of it. In that transitional area, you might get a false, not necessarily a false positive, but a false signal. And it takes a while for me to fiddle around with this sensor to get it in just the right spot so I don't get the hysteresis or switch bounce. So that's what that data looks like. I can recognize it and identify it. And another thing that helped me understand it was the data goes all the way out to here. And if I get my scale up and I bring that down, it's essentially 28, 29, 30 counts more than it should be. It should be 100. Well, if I count out each one of those little flat areas, it matches the overruns. So it is now fully understand what that problem was. It's always been in my test rig. So I went on, got that straightened out, and then I ran a number of runs again. And we've got beautiful straight lines, very, very straight, with little deviation from channel A and B on the left motor, channel A and B on the right motor, just nice, smooth, consistent, straight data. They're at different speeds, so I'm going to get different intensities or numbers of counts out of them. That's unimportant for this testing. Run 2, run 3 is the same, run 4 is the same, and then run 5, I did get an extra loop on the end of this, and I'm not sure exactly what the count was. It did go up to 101, but that could be just on when it gets triggered at the end of it. It might have triggered and then did a little run on and then had another on-off signal. I'm not going to concern myself with that. But because I did discover a problem with my methodology, I wanted to come up with yet another test run. And what I got to thinking is, what I want to do is put a little more practicality in the test for our next one. And for that, I'm going to take you to this one I'm calling the practical goal test. And it's based on this. The longest single distance to travel is 80 inches. That's the longest straight line road distance that the Zoomie has to travel. That's 2,032 millimeters. One wheel rotation is 5 inches, 262 thousandths and 2/10 of a thousandths, or 133.66 millimeters. Well, I want to replicate that in this next test. So if I take my 80 inches divided by 5.2662622, I get 15.2 rotations. That's the longest run the Zoomie will ever make without making a turn or something of that effect. So the test I came up with is to not just go 15 turns, but to double that. Let's go 30 turns without using the Hall effect sensor at all, other than as a visual marker for me to see that when I start the test and when I end the test, the magnet and the Hall effect sensor should be visually in line with each other. So we'll run 30 runs. We'll make sure that the magnet and the Hall effect sensor are in line. I have already run this test 9 times or 8 times, something like that. And so we're just down to the last few tests, so we'll run those real quick and look at that data. as you probably saw as I was fast forwarding through the test run, I'm copying text and data out of Thani and putting that in my spreadsheet. But let's take a look at what it means first. This is channel A and B for the left wheel, channel A and B for the right wheel. The right wheel isn't really part of this test. It's just another basis of comparison. For the way I plan to position, I'm only going to be looking at one of the two channels for each of the motors. So for example, I'm going to look at left channel A and right channel A. But why am I looking at channel B? Right now, it's a way of me verifying the data from one channel to the other on a specific wheel. The numbers should be the same. Any deviation between those two and the counts are getting off. So that can tell me a lot about the validity of the test. Further on, there's another little interesting aspect to what I'm gathering here. I take within the code up here, let me make all this bigger. This is the left channel A handler, and when the distance to go is less than or equal to 0 and mark state, a flag, is off, I am going to record that exact moment. Now that should be the exact period of time when the count is exceeded and I'm grabbing the last count of the run. Now there will be run on. I'm guaranteed of that because of delays in timing when I turn it off, as well as the momentum and the wheel and everything else to carry the motor forward as it decelerates to 0. And that is what this is about. Mark count is when it triggered in there, and by the time it finally stopped at these actual positions, specifically this one, left channel A, left encoder channel A, it overshot 23 counts. Now that's going to be important because I can never get it to stop perfectly. But if it's consistent, it's easy to deal with. And that's what we're looking at in our spreadsheets. So we'll start out, wrong one. Let me get to the other one. We'll go all the way over to here. I got to shrink this back down. This is the data that I'm copying and pasting, and these are the calculations for distance per count, distance of overshoot, and then in a metric equivalent here. But these are the deviations from channel A to channel B for both the left and the right encoder. It's always never more than 1 or -1. So we're really solid on that, and that's consistent across all 10 test runs. This is the data plotted out, and this red line is actually column A and column B, both of these. So that's another visual verification that channel A and channel B are giving me the exact same data, plus or minus 1 count. Very, very accurate, or we'd see the blue line come out from behind the red. Same is true of the encoder data from the right wheel. The green line straight. Well, you'll see this kind of drop off here. What's that about? That's the trigger when I start decelerating. Then the counts, of course, will be lower every cycle. So that's why you'll see that. And if we go through these, you will see very much the same straight lines dropping off at the end, like so, all the way through, all 10 runs. Oop, and I never pasted 10, so we'll have to skip that one. I'm sorry, it's just the 9 runs here. Or actually looking at it here, I had it, but I goofed up and erased the data, because there's the data from it. This data is that number right there, which is the inch amount of overshoot. If we're looking at that, you'll notice that it's fairly, let me zoom that up, it'd be a lot easier if you're looking. You'll notice that it's very easy, very consistent from one to the other. In fact, the average is 0.096 inches with a minimal amount of 0.0836, a maximum amount of 0.1064. Now, if I look at that 0.096, that's a lot. I don't want that much error. What I've been always targeting is a 0.5 millimeter. In the inch world, that would be 20 thousandths of an inch, which is slightly more than a 64th of an inch for those of you that like fractions. Now that's the average. That isn't necessarily real important, because if I know what is average, all I'm really doing is looking for the spread between minimum and maximum, because I could always, in code, have it, if I need to go 6,000 steps, stop that average amount less. Okay? It's a constant. It's consistent across all the data runs. So based on that, the only thing that matters is my range, which comes out to 0.0228, 22 thousandths and 8 tenths of an inch. Sounds like a lot, but we're at 0.579 millimeters, slightly over a 0.5 millimeter. I'll take it at this point. That result is really, really promising. Based on everything that I'm seeing so far, that's great data. Now, does that mean we're out of trouble and I'm ready to march forward? No. I'm going to probably do another couple days of testing. I do have either 6 or 12 more motors coming in probably this week. So I'm going to hold off, do testing on all those, see if they compare to this, and we'll move forward. Then from there, it's going to get real dicey for a while, because what I have to do, I have to completely change the way the current Zoomy control program handles positional data. This system will be very, very different than what I had with the AS5600 external encoders. So I got to really work through that very carefully, do a lot of testing with that, and then we'll probably catch you up at that point. So I suspect right now, if we don't run into more problems, that'll be the subject of the next video. Well, I know this video went real long. Hopefully it was interesting enough for you to follow along and stick with it. Again, I'm trying to keep these under 20 minutes, but to cover what I want to cover, sometimes it's going to go longer. Thanks for watching, and I look forward to seeing you in the next episode.